Hi, my name is Rémi and I am presenting the article entitled Curves with Fast Computations in the First Pairing Group. This was a joint work done with Sylvain Duquesne and Olivier. I'll start with a mathematical introduction, mainly to fixed notations. Then I'll move on to detail the motivations that made our contribution. Finally, I'll conclude with the results we've got when implementing and comparing to other curves. Let's begin with broad definitions of elliptic curves, pairing, and cyclotomic families of pairing-friendly curves. Let FQ be a finite field with at least 5 elements. An elliptic curve E is seen as the set of points x, y satisfying the equation y squared equals x cubed plus ax plus b, where 4a cubed plus 27b squared is not 0 in FQ. And that set is equipped with an identity element called point at infinity. Here, FQ bar denotes an algebraic closure of FQ. A FQ rational point is the point at infinity, or a point on the curve having both coordinates in FQ. The number of FQ rational points on the curve is q minus t plus 1, where t is the trace of the Frobenius morphism and satisfying the Hasse bound, that is, the absolute value of t is less than or equal to 2 times the square root of q. Let L be a prime number dividing once q minus t plus 1 and coprime to q. A pairing E of order L is a non-degenerate bilinear map E from G1 times GQ to GT, where all GIs are groups of order L. Over elliptic curves, pairing are usually instantiated as Veil or Tate pairing, for instance. The groups G1 and G2 are subgroups of the L torsion, that is, the points of order dividing L. G1 is more specifically the intersection of the group of FQ rational points with the group of L torsion. GT is the group of Lth roots of unity in an extension of degree k of FQ. The integer k is called the embedding degree of Q with respect to L. It is the order of Q mod L. Picking a random elliptic curve usually implies that k is about as large as L. As we want the groups GI to be secure, with, for instance, a 128-bit secure discrete logarithm, we expect L to be of size 256-bit, rendering the arithmetic of the finite field FQ to the k intractable. We thus have to be cleverer to select a pairing-friendly curve. We will use a generalization of the Bracing and Wayne construction, detailed in the taxonomy of Freeman, Scott, and Tesk, referred to as construction 6.6. This method gives Q, T, and L as polynomials with rational coefficients. BLS curves are examples of curves that can be constructed through this method. This construction 6.6 is said to define cyclotomic families of pairing-friendly curves as the order L is given by a cyclotomic polynomial. Let's sum up what we have seen so far. FQ rational points satisfy the equation y squared equals x cubed plus ax plus b, and there are q minus t plus 1 such points. We choose a prime L, dividing the number of FQ rational points. The embedding degree, K, is the order of Q mod L. A pairing is a non-degenerate bilinear map between three groups. G1, the group of FQ rational points in the L torsion. G2, a group of the L torsion different from G1. And GT, the group of Lth roots of unity in FQK. Finally, in construction 6.6, integers Q, T, and L are images of polynomials. Our motivation is twofold. Firstly, we contribute to the search of new curves resistant to recent advances on the number field sieve. And secondly, we shift the way a curve is chosen. We give incentives to pick curves that might have been otherwise discarded. Early 2010s, Barreto-Nering curves were widely used due to their optimality. For 128 bits of security, the target field of the pairing has size 3072 bits. That is, the curve is defined over a field of 256 bits, and the group of FQ rational points has order a 256-bit prime. In 2015, new variants of the number field sieve for computing the discrete logarithm in finite field were designed, and the final blow was given by Kim and Barbulescu. So in 2017, Barbulescu and Duquesne gave new parameter sizes for Barreto-Nering curves. They estimated that a 440-bit prime Q satisfies the 128-bit security level. Following their work, other curves, such as BLS, KSS, and Cox-Pinch curves, are into the spotlight as they usually have smaller prime field order. For a more comprehensive landscape, I urge you to check out Ororgevic website. The second point of our motivation comes from the fact that we decided to work towards finding curves fitting specific cryptographic scheme or protocol needs. A big family of cryptographic protocols benefits from a less expensive operation cost in the first pairing group. That family includes schemes such as group signature, direct anonymous attestation, enhanced privacy ID, and some accumulators. As an example, let's see more closely what it would mean for an EPID scheme. It is a privacy-preserving scheme that enables users to be authenticated and enables enhanced revocation of untrustworthy users. It is massively used to secure Intel SGX enclaves. So in that case, the signature is done by a constrained device. Upon signing, the device needs to show that it is not the issuer of any revoked signatures. That scheme does that through exponentiation in G1. Hence, we have an incentive to reduce the size of elements of G1 and the cost of exponentiation in that group. With both previous points in mind, one, the advances in discrete logarithm computation in finite fields, and two, schemes benefiting from a smaller G1, we can now detail our construction. As G1 is a subgroup of the FQ rational points, we would like a smaller prime Q. So the embedding degree and the prime L are picked in intervals such that the discrete logarithm problem is hard to solve in G1, G2, and GT. Thus, the real constraint is picking a prime Q of 5 machine words on a 64-bit architecture. That is, Q has between 256 and 320 bits. If L has precisely 256 bits and Q is ranging between 256 and 320 bits, the ratio log Q over log L ranges from 1 to 1.25. That ratio is also known as the rho value. Looking over to the taxonomy of Freeman, Teske, and Scott, that implies K is either 8, 11, 13, 16, 17, or 19. For embedding degree 8, the target finite field is too small. We found no solution for K equals 11. We've found only one solution for K equals 13. That solution has already been found by Orogevic. Curves with embedding degree 16 correspond to KSS curves, and Q is a 330-bit prime. Again, we found no solution for K equals 17. And finally, embedding degree 19 gave rise to one solution with the constraint we set on Q. That solution is an occurrence of construction 6.6 from the taxonomy. Q of x is a polynomial of degree 40, and L of x has degree 38. We set the equation of the curve to be y squared equals x cubed plus 31. The field of definition has 286 bits, and the groups G1, G2, and GT have order a 259-bit prime. To have a more convincing argument, we did some implementations and comparisons. The implementations were done using Relic Toolkit framework, and we inferred the naming convention of curves to name ours and Ororgevic's. The curve of embedding degree 13 is named BW13-P310, and the other of embedding degree 19 is named BW19-P286. Let's start with estimated costs of exponentiations in G2 and GT and of the computation of the pairing. We compared our curve to KSS, BLS, BN, and Cox-Pinch curve. They correspond to 128 bits of security and are already implemented in the framework. For the sake of simplicity, I am just going to compare the curve BW19 in blue to the BLS curve in red. We make the force estimations using a Karatsuba-like algorithm for field multiplications. That is, if a multiplication over FQ costs M, then a multiplication over the extension field FQN costs N log base 2 of 3 times M. Notice also that the time to compute a multiplication over the 286-bit prime field is half the time for the one over the 446-bit prime field. As expected, the cost of exponentiations in G2, GT, and evaluation of the pairing are greatly impacted by our choice of curve, particularly because we cannot use twists to express elements of G2 and cannot use tricks to reduce the cost of the pairing. So exponentiations in G2 is estimated to be 18 times slower on our curve BW19 than on the BLS12 curve. Exponentiation in GT about 1.03 times slower, and pairing 6 times slower. Moving on to the brighter side, we implemented the arithmetic of the curve BW19 in order to compare computation times. Notice that we have made benchmarks for 64-bit and 32-bit architectures, as we had in mind constrained devices. And our 286-bit prime is only 9 words on 32-bit architecture. Exponentiation in G1 is twice faster on the curve BW19 compared to BLS12 for a 64-bit architecture. And for a 32-bit architecture, it is about 2.5 faster on the BW19 than on the BLS12. We believe that a faster exponentiation in the group G1 and particular needs of some cryptographic protocols, for instance the enhanced privacy ID scheme, give an incentive to consider and switch to curves such as the proposed ones. Well, I thank you for having bear with me. Check out the article and contact me if you have any further questions. Take care and see you next time. Bye.